Okay, so we have studied and derived the energy equation. So I will ask you and encourage you to derive the other forms. That is, we have derived the energy equation that was having the Cp, right? That is, that was having the, I mean, that was having the temperature as the Eulerian variable. Okay. Now you can derive. I have also derived the E form, that is internal energy form. E form means the Eulerian variable is internal energy. Oh, okay. So I think I have denoted the internal energy by capital I. So that is the internal energy form. I have also derived the enthalpy form. So all these forms should be in your hand. Okay. So you should be comfortable with deriving all these forms. Okay. So now let us come to the application of this energy equation. Now in engineering, okay, so in engineering, as a thermofluids engineer, so let us say that you are designing an aircraft. Okay, so for an aircraft, the main two things, okay, from the mechanical force point of view, those are important. Okay, the main two things are drag and lift. Okay, drag and lift. Now in fluid mechanics, if a flow is there, so let us say that I have a flow and the flow direction is like this, and there is any body, okay, any solid body. Okay, so as an engineer, what my concern will be, that is, one, what is the drag, what is the drag, okay, and then maybe what is the lift, and also what is the heat transfer. Okay, what is the heat transfer. So as an engineer, I will be interested to mainly, I mean, find these things. Okay, so when you are designing an aircraft, so mainly the wing section. Okay, so in the wing section you have to, I mean, the wing is what generates the lift, right? So maybe the wing is looking like this is an aerofoil shape. Okay, and the, so the wind is coming like this. Okay, and it is generating some lift L, and also it is subjected to some drag. Okay, so now maybe due to some very high speed, okay, so when a space shuttle is landing or is entering in the earth's atmosphere, or other than the space shuttle, it may be a meteorite. Okay, so then due to its very high speed, whenever it is entering the atmosphere, okay, the temperature of the outer surface that increases, I mean, very rapidly. Okay, and that can cause a high heat transfer, right? So these things are of primary importance as an engineer, right? Now how can we calculate the drag? So now let us come to a very standard case of a flat plate. Okay, so let us say that this is a flat plate I am drawing, right? So this is a flat plate and the fluid is flowing over this, right? And we have the no slip condition valid. Okay, so no slip condition is, I mean, not necessarily the no slip condition has to be valid. There are cases for some rarefied gases, so depending on the Knudsen number. Okay, if the continuum hypothesis is not even valid, then the no slip condition will not be valid. Okay, in microfluidics also there are various cases where the no slip conditions are not valid. Now in this case, for a macroscopic flow and considering the continuum hypothesis to be valid, uh, the no slip condition is also valid, and as all the fluids have a finite value of the coefficient of viscosity, then we have something called a boundary layer, right? So a boundary layer is what? That is, at this position, that is on the interface of the fluid and the solid, that is the surface of the solid, at this position we have V equal to, so this is the let us let me first draw the coordinate axis x, and maybe this is the y. Okay, so this is the y. Okay, so x and y, so Vx, this Vx, this will be V solid. Okay, that is, at the boundary the tangential velocity of the fluid, the with respect to the solid, that is 0. That means what I am saying is, so this is Vx of fluid. Okay, so that is Vx fluid minus V solid. So this must be 0. Okay, that means if V solid is 0, so if this is 0, that means Vxf is 0. Okay, so this is the no slip condition. So considering that the plate is held fixed, okay, so this is the 0 velocity, and we have something called viscosity, right? So viscosity will propagate the information that yes, there is a wall, and some particles have come to rest. Okay, and these particles are now in rest, so these particles will retard the above layer. Okay, so before entering to the plate I had this uniform velocity, now I will have, this is at 0, so above this particle the velocity will have some value. Okay, so now let me draw uh, reference y direction, so maybe with the red color. So this is the reference y direction, and the velocity will be, okay, so this is 0, and maybe above this will have some value, and above this will have some greater value. Now I have reached a point above which this viscous uh, I mean this viscous information, or the information that the wall is present, that will be not propagated. Okay, so above this point I will have the normal velocity, that is, the free stream velocity u infinity. So this length is called the boundary layer thickness, right? This length is called the boundary layer thickness delta, right? Now if I take another section here, right, if I take another section here, then what will happen? So let me do a very interesting analysis, that is, if I take this height, okay, so at this horizontal level, maybe this is at point A, at this is at point B. So at point A, at this horizontal level, the velocity was something, let us say that this arrow is depicting the velocity v1 or va maybe. Okay, so now at point B, the fluid is now, the fluid has come a lot on the plate, and because of that the information that the plate is there, that will be propagated more and more to the fluid. Okay, so now, and that is why this velocity will be lesser. Okay, so this velocity will be lesser than this. Okay, and this will be along. So uh, and here it is 0, and if I join this, so this will be the velocity profile. Okay, this looks like it is linear, but it is not. I mean, it can be linear, it cannot be, that at this point we don't know that. Okay, so this is the velocity profile, this is the velocity profile, right? Okay, so and after this position, so this is the length, vertical length, that is delta. So if this is delta A, then this is delta B. So two things, that is uh, delta B is greater than delta A. Okay, and also let us say that this height is something, a characteristic height y bar, any arbitrary height. Okay, so at y bar, okay, so V at section A at the height y bar, this will be more than V at section B at height y bar. Okay, so now boundary, and I think that the reason for this is clear, that as the fluid is moving more and more on the plate, the information that the plate is there, or the viscous retardation at the same y level is more. Okay, and that is why at the same y level the velocity will be lesser. Okay, and that is why the boundary layer actually is growing, right? That means uh, understand this thing, that we have two extreme velocity levels which are same for both the sections A and V. What are those? One is at y equal to 0, we have this V equal to 0, and at at somewhat distance we have u equals to uh, u infinity, that is the free stream velocity. Okay, so from this 0 value you have to reach u infinity. Okay, so at this A, the fluid has just entered on the plate. Okay, so at this characteristic length y, this y bar, okay, this velocity is Va, but now at this section B, this velocity at y bar, this has decreased. Okay, so now it will take more time to reach or to increase at the value u infinity. Okay, so that is why the boundary layer thickness at delta B will be more. Okay, so if we join the two locus, so at this point it is reaching u infinity, at this point at A it is reaching u infinity, and at every section I will have this kind of points, and if I join all those points, then I will get what is called as boundary layer thickness, or boundary layer. Okay, thickness is delta. Okay, so we have to keep in mind these two things. These two things are primary. Okay, now you may have already known you may have already know all these things, right? Maybe you have studied fluid mechanics in great detail, but as I have commented that I don't want that I mean, you have to look for any other thing that is required for this course from any other source. Okay, that is why I am trying to cover from as much basic as I can. Okay, and so beyond all these things, if something is remaining, that is you so I mean, a very pivotal concept you might not be knowing, then you should comment in the comment box that please let me know that how this thing comes. So if I have already covered that in my fluid mechanics course, then I will then I may tell you to refer to that. And if the concept is very important, okay, or if I haven't covered that in my fluid mechanics course, then I will surely cover that in my upcoming videos. Okay, so now let us move forward. Now, this was the boundary layer, and why this is important at all. Okay, so the concept of boundary layer was proposed by a very famous fluid dynamicist, um Ludwig Prandtl. Okay, now you may think that why should I study all these things? I could have simulated the flow by a very detailed CFD analysis, right? Now let us see that I have told you that the shear stress in the previous video. So for a Newtonian fluid, okay, so let me write with another color. So for a Newtonian fluid, right, shear stress, okay, tau, okay, so tau ij, I am writing in indices notation, is minus p plus lambda del u k del x k delta ij plus mu into del ui del xj plus del uj del xi. Okay, and so after some simplifications, that is for incompressible flow, okay, we have tau ij equal to minus p delta ij plus mu into del ui del xj plus del uj del xi, right? Okay, so now maybe I require, now let us, okay, so let me draw the plate again freshly. So this is my plate. Now I am not drawing the plate by two lines, so let me make it a single line. Okay, so this is the boundary layer and the flow is incoming like this, and the coordinate axes are given by these directions. So this is x and this is y. So this is y, sorry, okay, and this is origin, right? So drag means what? So now I am telling that the plate is held fixed. Okay, so just apply your common sense that if let us say that you are having a small piece of paper, right, maybe a cardboard. So if you spray some liquid or water with sufficient force on the cardboard, then the cardboard will move, right? Then the cardboard will move. So, and how can it move? That is, the fluid is dragging the cardboard. So in these few sentences there is no uh, mathematics, no rocket level science. These are the experiences of our daily life, right? That means there is some drag force that the fluid is applying on the plate, right? So this drag force is arising, okay, because we have the property viscosity, that is the fluid friction. Now, sorry, okay, so at this level it is y equal to 0. Okay, so at y equal to 0 I have some viscous stress, okay, that is tau. So at this point I have tau wall, so this is wall shear stress. So drag, FD, drag force, that will be wall shear stress into area, right? Now if the wall shear stress is constant throughout the length, then this formula will work. And if the wall shear stress is varying, that is, if this is a function of x, then Fd will be, so this is a function of x. So if I take a small elemental area, I mean length dx, so into dA, and that dA will be b into dx, where b is the width. Okay, so integral of this over some length L. Okay, okay, so that means this tau wall is our primary importance. Now here this tau wall is applicable in this x direction and on a surface that is denoting, I mean that is having a normal in y direction. So x direction means x1 and y direction means x2 in indices notation. That means this tau wall is nothing but tau xy, and that is equivalent to tau yx considering no body couple. Okay, so these things I have derived in the energy equation. Okay, and in indices notation these are 1 2 2 and equivalent to 2 1, right? So if I put this in this expression, then it is tau 1 2, so delta 1 2 is 0, so this will be mu into this du1 dx2 plus du2 dx1, right? So this is the drag force, I mean this is the wall shear stress. Now this is not the wall shear stress, because for uh, for it to be wall shear stress I have to write at y equal to 0, at y equal to 0. Okay, so okay, and in xy notation tau xy at y equal to 0, so this is tau wall, this is du, okay, du dx, du dy plus dv dx at y equal to 0, right? Okay, so that means I have to somehow calculate these gradients. Okay, so we will see that this dv dx component will not be important. So so when it will not be important if the v is very small tending to 0, that is very small, or the x is very large. Okay, so then it will be not important. And like if it is a, like in this flow, okay, this v is not very important. Okay, so we will see in our analysis that if this v is not important, then this tau wall directly boils down to mu into du dy, right? So that means now this is the u profile, this is the, okay, let me draw it here. So at any section, I have taken this section, okay, at any section I have a velocity profile like this, right? So this is the u profile, x component of velocity profile. Okay, so now this du dy at y equal to 0, okay, so this is at y equal to 0. So du dy del u del y at y equal to 0, that is nothing but the slope of this velocity profile at y equal to 0. So the slope is nothing but this thing, right? So let me draw it with another color. Okay, so this is the slope. So if this is the angle, and this line will be the slope theta, so del u del y is equal at y equal to 0 is equal to tan theta, right? Okay, so essentially I have to find this velocity profile, I mean no, not the velocity profile, essentially I have to find this thing, So I have two options. So I can find it directly, or I can find the velocity profile, then I can find the del u del y, right? So I can do this analysis. That is, I can find the velocity profile directly, okay, and I can then I can find the slope, and or I can find the du dy directly. So we will see that uh, how we can approximate the velocity profile and we can still get a very accurate du dy. Okay, so as a fluid dynamicist, we may be interested in finding the appropriate and accurate velocity profile, but as an engineer, if someone can give us the value of du dy at y equal to 0 without finding the velocity profile, then also we accept that. Okay, so and now I must tell that in some flows this dvdx can also be important. Okay, so if that is important, then you have to take that also into account. Okay, but for an predominantly one dimensional flow where the variation of v is not important or maybe very low, so there you can apply this thing. Okay, that is dv dx is neglected, del v del x is neglected, right? Okay, so this was that how can we calculate drag, and that is why we need something called a boundary layer. Okay, because in the boundary layer only we have to find this velocity profile by the boundary layer analysis. Okay, and I will show you that how the uh, that how the how the velocity profile is being, sorry, how the Navier-Stokes equation, okay, is simplified. So we don't have to solve the full Navier-Stokes equation to get the velocity profile in the boundary layer, but we can neglect some of the terms, and that is the contribution of Ludwig Prandtl, and which is known as the Prandtl's boundary layer theory. Okay, now I have talked about the drag. Now what about the heat transfer? Okay, so again let me draw the same flat plate. So this is the flat plate. Okay, the same fluid is flowing. Now the situation is, okay, so this is having a temperature T infinity and U infinity. So if this plate is also having the temperature T infinity, then no heat transfer will happen at all. Okay, but if the plate is having a temperature something T wall which is either greater or less than, I am considering here greater than T infinity, then the heat will be transferred. Okay, now for the no slip condition, the fluid particles which are adjacent to this wall, those are not moving, those are at zero velocity with respect to the plate. Okay, that means there will be some heat conduction from the plate to this fluid particle, right? So those who already have heard or have done some course on convection, they must be thinking that convection means I have some movement of fluid. So here the movement of fluid is over the plate. Okay, so the mode of the heat transfer should be convection only. Okay, so let me tell you that convection is not any unique mode of heat transfer. It is just advection plus plus conduction. Okay, I think I have talked about this during the derivation of energy equation. Okay, that is the primary mode of heat transfer is still conduction, and it is assisted by the fluid flow. That is, you can consider that here I have a fluid particle, and by conduction the heat is transferred here, and now the fluid particle is moving and it is carrying the heat. Okay, so the heat transfer mode is still conduction, but this movement of fluid particle, this is assisting the heat transfer. Okay, now and so what I am saying is, again I am drawing my coordinate axis, x and y is origin. So at y equal to 0, okay, I am having the heat transfer by conduction. So for the fluid, if I have a temperature profile, so what will be the temperature profile? It will be something like the same, that is, at this point the temperature will be something like Tw. So Tw will have a large value. So let me show it by a red color like this. Okay, so this is Tw. Then the temperature will be decreased. Okay, again it will decrease, and at some point of value it will be T infinity. Okay, so and at different section it will be different, right? And if I joined all these points, this is my thermal boundary layer. Okay, similar concept to the hydrodynamic boundary layer. So this is my thermal boundary layer, right? And if I joined all these points, so this is the temperature profile at a section. So this is the section maybe at A, right? So at y equal to 0, the gradient of this temperature profile in y direction, that is dy. So if it is a Fourier fluid, so into Kf, that is the thermal conductivity of fluid. So this is the heat flux. Okay, and that will be, okay, so that will be the heat flux or the heat transfer q double dash. Okay, so if this is the q double dash, and from the point of view of convection, we define something called a heat transfer coefficient, such that the heat transfer coefficient into the temperature difference of the wall and the free stream temperature of the fluid into the temperature into the heat transfer coefficient, that should give us the heat flux. So this equation is what is depicting the uh, contribution of convection. So this is convection heat transfer coefficient. So this is the convection heat transfer coefficient. Okay, so this is H. That means we have, so if we have to find this q double dot, okay, so our, as an engineer, our objective is to find this q double dot, and that we can find by finding this at y equal to 0, that is the temperature gradient del T del y at y equal to 0. And if I have to find that, again I have two options. If somehow I can find this temperature gradient at y equal to 0 only without finding the temperature profile, then also I am done. And the another option is, that is more accurate, I have to find the accurate temperature profile, then I can find this gradient at y equal to 0. Okay, so in engineering applications this H is mentioned. Okay, because if I know the H, then for any T wall and T infinity I can find the Q naught. Okay, and so let us see one thing, that is, if now what I am doing is I am non-dimensionalizing the temperature and the y. So theta is T minus T wall by T infinity minus T wall. This is theta, my non-dimensionless temperature profile, and eta is y by delta T or maybe y by L, any characteristic length scale LC. Okay, y by LC. I will talk about what do we mean by characteristic length scales. Okay, so if I now substitute this in here, okay, so how to substitute very quickly? Just see that del T or dt will be what? Del of theta into T infinity by this by, okay, plus this, right? So this is a constant, this is a constant, so this will be this into d theta and plus dtw, but this is 0, right? So you can see that it is like the actual variable is t and something is, I mean t by something, t by another reference temperature, that is giving us the non-dimensional temperature. So in the actual equation I have to write, instead of del t, it will be del theta into the denominator of the non-dimensionalized temperature. Similarly, you should now be comfortable that this del y, this will be changed as del eta into this LC. Okay, so maybe I am having some another uh, non-dimensional parameter xi equal to x by some L, okay, by BC. Okay, then this del psi will be what? I sorry, I mean this del x will be del psi into this BC. So just you have to multiply the denominator into the side. But here, if this T wall is also varying with the uh, x, then this del T, so this will not be 0 and this will also not be a constant. So these things will be, I mean, should be taken care of. Okay, that whether this another factor, that this is some offset, okay, from t, so this factor if it is a constant, then this is 0, that is okay, but if this is not a constant then we cannot write as this. So we will take up various cases, that is when the tw is constant and when it is not constant. Okay, so for this case, if I now non-dimensionalize this equation, then it will be del theta del eta into t minus, okay, so t infinity minus t wall, and minus sign is here, by LC, this will be equal to what? H into t wall minus this. So I can absorb this minus sign and this will be plus and this will be minus. So if I cancel this out, this and this, okay, and I think I have missed the kf, k of fluid, so this will be what? At eta equal to 0, because this was at y equal to 0 and at y equal to 0 eta is also equal to 0. So this will be what? HLC by kf, right? And this is a number that is called Nusselt number. I think most of you have already known, I mean most of you have already studied all these things, but if there is one student, I mean even if there is one student who has not studied these things before, for him only I am covering all these basics. So this is called Nusselt number, denoted by Nu. You can see that this Nusselt number is nothing but HLC, okay, so HLC by kf, I can write it as, okay, H delta T, C some characteristic delta T, okay, and into okay, so let me write it like this, that is this is some LC by Kf into delta T, right, and some area C, constant area. Then I have to do some here also this, okay, and okay, so delta Tc I can omit. Okay, so now this is what? This is the conduction resistance, right? And this is what? The convection resistance. So this is essentially the conduction resistance versus the convection resistance for a fluid flow. And we have something very similar, that is HLC by Ks, that is K of solid. This is called the bio number. Okay, so don't get confused. For bio number, this is Ks, and for Nusselt number, this is Kf, K of fluid. Okay, okay. So as an engineer, I have told that I am interested in H, and so for any, I mean, in various engineering applications, the LC can change the characteristic length scale, and the fluid can also be changed. Okay, so apart from H, as an engineer, I am concerned about the Nusselt number, which is an indication of the parameter H, and that will give us the value of heat flux. And I can see that the non-dimensionalized temperature gradient is the Nusselt number. The non-dimensionalized temperature gradient at y equal to 0 is giving me the Nusselt number. Okay, so in this total course, our main objective will be to find the Nusselt number. Okay, so now our first case that we will solve is the external convection. Okay, so there are many other things, like um, we have something called the Reynolds Colburn analogy. Okay, and that is, you see, I mean, I will derive this step by step in my upcoming video. Okay, but you see that you should try it yourself first. That is the equation of, I mean, governing the energy equation in terms of temperature, and the Navier-Stokes equation in, so okay, so just I mean, it is very interesting, just in my mind it came. Okay, so the energy equation, what it is. Okay, so I mean, neglecting the viscous dissipation, and for an incompressible flow, the energy equation boils down to what? Del T plus U del T del X plus V del T del Y is equal to alpha this thing plus this. Okay, this is the energy equation, and Navier-Stokes equation is del V del T plus, okay, so maybe I am okay, so this thing for a two-dimensional flow, okay, plus U V del V del X. Okay, so let me omit the vector signs. So this V can be anything, U, V or W. Okay, so this is equal to nu, okay, this is nu into, so if the pressure gradient is 0, I mean, plus this. So after various assumptions, we are getting these two equations, and you can see that these two equations are very similar, right? Mathematically these are exactly similar. exactly same. The mathematical form is exactly same. Now if the boundary conditions are also same, then we can say that the two differential equations are exactly same. Thus the value of alpha and mu, if those are same, then those two equations are exactly same. Then we can correlate the solutions of temperature and velocity, and temperature can give me the heat transfer coefficient H, and velocity can give me the friction coefficient Cf. So from this analogy I can get uh, some relationship between H and Cf. Okay, so this this is known as Reynolds analogy. Okay, so this is very important. Now what your task is, consider these two equations, and you will see that the boundary conditions of these two equations will not be same. To make those same, you have to apply the non-dimensionalization of the temperature profile, just to make the boundary condition look similar. So T will be replaced by some theta. This theta you have to choose that what it should be, and your objective is to make the boundary conditions of both the equations same. Okay, so and then you can solve this equation maybe, and you can get the solution of this equation, and that means you are getting mu into du dy at y equal to 0, that is equal to some what it is, k into del v del y. Okay, k into del t del y at y equal to 0. So not mu into, because mu and k are not in the in the equation. They are in the equation, but primarily I can say this. If the solutions of both the equations are same, then primarily I can say this. Then I can multiply with mu. Okay, so then this will give me what? Tau wall, and this will give me mu into del t del y. But if I can do one thing, that firstly I have to change this t, so this will be changed by theta, right? This will be changed by theta. So now if I do one thing, that is mu into kf by kf into del theta del y at y equal to 0, then you can put some variable instead of y, eta. So eta into some LC, so this will be some LC, right? Then this is nothing but your Nusselt number, right? And Nusselt number means H into kf by LC. Okay, so then we can see that we are getting some expression between H and this tau wall, and tau wall can be, I mean, Cf means what? Coefficient of friction is tau wall by half rho u infinity square. Okay, so tau wall I can write is equal to Cf into half rho u infinity square. Then I can correlate this Cf and this H. Okay, so this is the Reynolds analogy. So this is totally a mathematical exercise, and you should try this. Okay, and I will derive this, okay, step by step in some upcoming video. Now let us proceed. I am removing this because this is actually not the part of this video. I have just uh, given you the introduction so that you can proceed for this part by yourself. Okay, so now the topic that I will be covering is the what? Forced convection over a flat plate. Okay, so I will be taking up this topic from the next video onwards, and the same problem, that is on a flat plate and incoming free stream will be there, and we have to estimate the value of the Nusselt number, the drag, everything. Okay, so I will take this problem from the next video, and this was just an introduction. Okay, so if you have any comment or any doubt, please feel free to share those in the comment box. If you feel that I need to improve in my teaching style, then you can also tell me that if I am going very fast and if I am going very slow, anything. Okay, so feel free to share anything with me. I will try to help you guys as much as I can. Okay, so until the next time, bye and take care. Thank you.